We're going to talk in this video about how in a Boolean algebra we can represent the operations of or and, join and meet completely in terms of mod 2 arithmetic, assuming our Boolean algebra is finite. So Boolean algebra, you could think of it as a post set, so partially ordered set that has a top and a bottom. And you can always meet and join any two elements, and meets and joins actually distribute over each other, and there's a unique way to get complements. Now, anything like that with those properties actually gives us something that's like a power set. In fact, you can make a bijective map to a power set that actually preserves these operations. So we say it has the same structure. Anyhow, so we can think about power sets and finite Boolean algebras in the same way. So if we have a power set, then we're thinking about subsets of set. So let's suppose the set has maybe like 5 elements in it. 1, 2, 3, 4, 5. So we can think about codes representing the subsets, codes of zeros and ones. So if I have a subset that has 5 elements, maybe I have a code that looks like this. This means that I'm thinking about a subset that has this element, and that element in it. So it'll be a subset of 3 elements, the first element, the third, and the fourth, if I had listed them out in order in 5 different positions. Okay, so we're already thinking about ones and zeros here. Now, let's think about how we can describe the arithmetic of meet and join in terms of mod 2 arithmetic. Now, for power sets, this is the same thing as intersection, and this is the same thing as union. Let's start with this one right here. What if we had a subset that looked like this? 0, 1, 1, 0, 1. And maybe we have another one that looks like 1, 1, 0, 0, 1. And we would like to perform this operation. So we're going to meet them, or it's like finding the intersection. Well, pretty much if we just multiply down component-wise, let's see, multiply down, you get, like, think of this as multiplication mod 2 in components. So thinking of this as like an ordered 5 tuple in z mod 2z 5, then really we're just performing multiplication component-wise here in this ring right here that has addition mod 2 and multiplication component-wise across. So think multiply down. We have 1, multiply down 0, 0, 1, 0. And notice it is the intersection. What's common between the two sets? It's just multiplication component-wise. Now let's think about how we would perform perhaps the same thing here between. So let's see how we can do this. If we want to do 0, 1, 1, 0, 1, let's just stick with the same two subsets here. And let's perform this operation. Now this is going to happen in 2 stages. All right, we actually did one of them right here. And now the other one, we're going to simply do addition in this ring, okay, just component-wise. So we have 0, 1, 1, 0, 1, 1, 1, 0, 0, 1. Let's just add in this ring. So we have, okay, so we have 0, because 1 plus 1 mod 2 is 0, 0, 1, 0, 1. Okay. So now we have this. Okay, so then let's take this result right here and this result right here, and let's just add them together using mod 2 arithmetic. So if we add them, notice that we get, so in the first component we get a 1, second component we get a 1. Third component, we get a 1. Get a 0 in the next component. And then we get a 1 in the next component. Notice we did the union successfully between these two subsets. So basically what we did is we did, and we could think of this, if you like, maybe I'll rewrite that as multiplication. Okay, so that's multiplication right there. So we multiplied, we added, and then we added those two results together, and we get the union, or the join rather, here. So meet and join can be expressed completely in terms of just the natural ring structure with addition and multiplication in z mod 2z 5. So that's z mod 2z cross z mod 2z cross dot dot dot. So we have 5 of them. Okay. So now, if we want to take a look at something, at a picture, this is a Hasse diagram for a Boolean algebra that's represented by a power set on 3 things. So these are the different subset codes. Okay, let's just think about using, about quotienting. So like a quotient of our Boolean algebra with a chunk, okay, right here. This is actually a subgroup of the whole thing as a group. I mean, thinking about this z mod 2z, actually in this case z mod 2z 3, right here, we have this Boolean algebra is the same thing as this, and we can think of a subgroup here. In fact, this right here is a subgroup where we have these two components being 0, and then this component can vary. So we're basically just looking at the first component only. And that's a natural subgroup. Not only is it a subgroup, but it is an ideal. Because if you think about it, if you multiply, right, and you have these zeros here, if you multiply component-wise, you're always going to have zeros in these last two components if you multiply anything in. So it's closed under multiplication. If you multiply this element to these, you stay in here. This element to those, you stay in there. It's completely there. In fact, because meets and joins are expressible in terms of this ring structure, and actually vice versa. This ring structure, the multiplication addition, can actually are expressible in terms of meets and joins. If you want to have a nice merge, meaning like a partition into chunks, where you have a quotient that induces a nice operation of meets and joins between the different chunks, it really is equivalent to taking a quotient of this ring. Now, quotients of rings are done by ideals. This is an ideal right here. Its cosets, additive cosets, represent the different chunks. So take this and let's think about it. What would happen if you take this and added this element to each one of these guys? So you shift this. It's an ideal as a subgroup too, right? This subgroup of the whole thing, this as an additive subgroup, and you shift it by this. So you add this to each one of these guys. So if you add that to this guy, don't you get that guy? Add this to this one, don't you get that one? Yes, this whole thing, this chunk right here is an additive shift of that one. It's also a union shift, if you like. If you union this element to this guy and this guy, you get that whole thing. So it's both, you could think of it as a union shift, or you could think of it as an additive shift right in here. So we've been talking about mod 2 addition here, component-wise. That's actually equivalent to the symmetric difference between two sets. So that's another way of thinking about it. But it's kind of fun to think about everything in terms of mod 2 arithmetic. Thanks for watching.